Physics students, good afternoon. Today in this video we're going to be looking at some more applications of the work-energy theorem, a relationship that we've been talking about in class over the past couple of weeks. Here, specifically, we're going to be looking at an example of when a force does negative work or removes energy from a system. So this problem is specifically geared towards number 14 on your homework over work energy. We're going to go ahead and read the statement. It goes like this. On a frozen pond, a 10-kilogram sled is given a kick that imparts to it an initial speed of 3.3 meters per second. Excuse me. The coefficient of kinetic friction between sled and ice is 0.15. Find the distance the sled moves before coming to rest. The acceleration of gravity is 9.8 meters per second squared. So here, as we've done a lot in some of these different videos, and as we do in class all the time, it's very helpful to try and visualize what's going on. So I'm going to go ahead and draw a picture. Okay, so we're going to get a kick onto, let's say, the pond. So here's our sled. We get a kick, and our sled kind of begins moving across the pond until eventually it comes to a stop. Okay? So we'll say this is kind of when the kick occurs, gives it some velocity. We're told that it begins moving at a velocity of, my number is 3.3 meters per second. And at the end, we'll say this is our initial velocity. At the end, it comes to a stop. And our job is to figure out how far it goes before it stops. And we usually refer to that how far value as delta x. That's what we're asked to solve for here. How far is the object going before it comes to a stop? Now, as we've talked about, typically, force that causes an object to come to a stop when it's in motion is what we would call friction. So we're told that the coefficient of kinetic friction, and kind of how the roughness between the sled and the ice, is 0.15. So I'm going to write that in just by my picture so that I have it for reference. We're told as well the mass of our sled is 10 kilograms. And that's a number that we might need, so I'm just going to go ahead and write it in. So I have kind of all the numbers that I'm given. Now, we're told to find the distance the sled moves before coming to rest. Now, when finding this distance, this seems like it's going to be maybe something like a kinematics problem, right? Where we set up Newton's second law, we maybe find an acceleration, we use the kinematics equation to solve this. Now, you're not told directly what method to use, and if you feel more comfortable setting this up to find acceleration and then using that to use the kinematic equation, that's okay. And we're going to solve this using the work-energy theorem and show how that's also a way we can solve this problem. But again, if you want to use kinematics to set that up, that's just fine. So here's what we're going to do. I'm going to write out my equations for work and energy. So work done is equal to force times displacement, cosine of the angle between them. We've also said that work done is equal to a change in energy. Now here, we should be able to identify energy that's changing, right? We're starting with some velocity, we're ending with no velocity. Okay? So friction is removing energy, it's doing work on our sled. So we could use this approach right in here to find the work done pretty easily. Okay? And that's what we're going to do to start. We're going to find the work we have initially and the work we have at the end. So here's what let's do. We'll say our energy to begin is all kinetic. We're just moving on flat ground. We're not really told anything about a spring here. So our initial energy is all kinetic, 1/2 mv squared. Now our final energy, if we're on the ground, we're not moving, well, we don't really have any energy. So we have 0 joules there. So let's plug in the values that we know. They are kinetic energy initially, 1/2 times our mass, which we said was 10 kilograms, times our initial velocity, 3.3 meters per second, squared. So we'll take a moment and plug that in. 1/2 times 10 times 3.3 squared. And so our initial energy, which is all kinetic, is 54.5, I believe, joules. So So we start with 54.5, we end with 0 joules. So we would say the work being done here is negative because we are taking something out of our system. So the work done is equal to our change in energy, negative 54.5 joules. And it's being removed from our sled. So if we use that, remember what we're trying to solve for. We're trying to find how far the sled goes, this delta x, right? Now, in order to do that, we need to look at the force, right? And here, well, the force that's going to cause us to do that, as we're told, is friction, right? So what we need to do is we need to find what is that force of friction, and then use that in our work equation to find the delta x, how far that object moves before it comes to a stop. How long does it take friction, really, to take all the energy out of the sled? Now, because we are dealing with a force that is doing negative work, that is also going to come into play with our angle. And we'll talk about that here in just a little bit. But we're going to take this value for work, and we're going to come back to it here in just a moment. Now, we'll come to a new page, and we're going to look at the frictional force. So, I'm just going to draw a very generic picture of my sled. Now, our sled is experiencing a gravitational force. It's experiencing a normal force. And we'll say after it's kicked, the only force in the horizontal direction we'll say is our frictional force. So effectively we'll say we're kind of moving this way to show that friction's working against us. So we kind of talked about this a little bit in one of our earlier videos. Remember, frictional force is equal to our coefficient of friction times our normal force. So to find our frictional force, we first need to find the normal force. So if we look at what's going on in the y direction, here's some things that we know. Newton's second law, sum of forces in the y direction is mass times acceleration. Now we're told pretty straightforward in this problem that we're moving across a horizontal pond. We're just kind of moving across the pond. And if we do, we're not really moving up or down here, so we can assume we have no acceleration in the y direction. And what that tells us is that if we're not accelerating, these two forces, normal force and force of gravity, have to be equal. So Fn is equal to Fg, which we know our force of gravity is just mass times gravity. So we're going to take our mass, multiply by g for the Earth, we'll find our normal force. So normal force is 10 kilograms times g for the Earth, 9.81 meters per second squared. So if we plug that in, that's going to give us a normal force of right at 98.1 newtons. Now that's not our frictional force, but it's the way that we find our frictional force. We're going to take that and plug it in here. So our frictional force is our coefficient times the normal force. So Fk is equal to our coefficient, 0.15, times the normal force, 98.1 newtons. So we'll take that value, 98.1 newtons, and multiply by 0.15. That's going to give us our frictional force, a little bit lower, which seems reasonable, 14.7 newtons. So now we have our frictional force, which is the force doing the work. That's what we're going to use. We have the work that's being done, and now really all we need to do is figure out, well, how far is that object going to slide? How long is it going to take friction to remove all of this energy, do this work? So what let's do, let's come back to what we set up. Work, now we're going to use our second approach. This is a great problem where we can see both approaches being used. Work done, which we already solved for, is equal to our force, displacement, cosine of the angle between them. So I'm going to rewrite that equation down here, and we'll begin to solve. So work done is equal to force times displacement, cosine of the angle between those two. Now we said here that friction was doing negative 54.5 joules of work on the sled. And that's because friction is taking away its kinetic energy. Work is a transfer that can be positive, adding in, or negative, taking out. And this is equal to our force, F, which we just solved for, which was 14.7 newtons. Okay, we don't know delta x here. And then cosine of the angle. Okay? Well, here's what we have to think about. Okay? If we're moving one direction, right? This is the direction of our displacement. Friction is working, remember, against us. Okay? We've talked about this before. We're moving one way, friction's acting the other way. Okay? So there's a 180-degree angle between those two. And we said cosine of 180 is always going to give us -1. And that's an important value. Because what that's going to do is that it's going to ensure that our displacement is positive. And we know that because we're moving in what we've defined as the positive direction. Excuse me. So what I can do is I can go ahead and kind of cancel that negative out on both sides of our equation. So I'll go ahead and rewrite it this way. And you can kind of cancel out the negative. 54.5 joules is equal to 14.7 newtons times delta x. So now, in order to get delta x by itself, I'm just going to divide the work by our force. So I'll divide by 14.7 newtons on both sides of our equation. 14.7 will cancel out on the right-hand side, and we'll be left with a delta x value, a displacement, of 54.5 divided by 14.7, and that gives us a value of about 3.7 meters. So roughly in a range of about 10 to 12 feet, which seems pretty reasonable. We kick the sled, it's going about 10-ish, well, about 7-ish miles an hour, and we finish by going a distance of about 3 to 4 meters, roughly kind of 10 to 12 feet. So hopefully this kind of gives us another good application of that work-energy relationship and how we can now use really both approaches to solve kind of a complex style problem. And hopefully this will get you started working through problem number, this was 14. Best of luck.